After a nice summertime here in Europe, I feel good to start for the fall with the expert talk, and later the year at Christmas or prior to Christmas have our wide bandgap conference in Munich at the Hilton Airport. So that was just a few words prior to the introduction. I welcome all the ladies and gentlemen to the expert talk. I will be staying in the background. The moderation will be done by Alfred, so I can relax and watch what's ongoing. So, Alfred, it's your turn.
Thank you, Bodo. I will take over. I will not only take off my hat, but here I am. Welcome, everybody.
Still hair.
Yeah, that's right.
Except
but it's gray, more gray than black. Anyway, we are very glad that you are here with us. And shall we wait another minute, probably, until everybody will have logged in, or what do you think? We're almost ready.
I have a question.
Yeah, Pierre?
So to introduce the article, I have made a short presentation. So is it okay to share my screen or?
Yes, of course.
Okay.
Everybody's got 15 minutes. And everything that contributes to explaining more in-depth information about the article and the contents would be much appreciated. And then we should still have some time for questions from the people who are joining us here in the live stream.
Okay.
All the visitors, we talked about that all the presenters should shortly give a rough summation of the topic of the article. Sometimes the visitors just saw only one or the other article, and so it could be a help.
So I think now we have waited long enough for all those who joined us a little bit later. Now it's time for Dr. Daniel Martin from Wolfspeed to talk a little bit more about his article that was published in our April issue about a 1500 volt DC link architecture, which is essential to solve the need for more power. Dan, could you please go ahead and explain in a few words what your article was about and what it deals with and what it specifically outlines?
Yeah, absolutely. Thank you. Can you hear me?
Very good. Thank you.
Absolutely good.
Excellent. Yep. So, I mean, the basis of the article is, you know, as we're putting more and more power onto the grid, right? We're often seeing that it comes from renewables to be able to address a very short time cycle for that to occur, instead of installing a new power plant or new distribution to get to a remote site. So we see a big explosion in terms of demand for this type of market, especially when it comes to now, it seems to be shifting towards data center power. And, you know, the solar industry has established this 1500 volt DC link just to be able to get the most out of the panels. So when it comes to an inverter to the grid, you know, you have to be able to withstand 1500 volt DC link, energy storage systems that are connected to that intermediary DC voltage also have to handle this. So we see the industry has moved to 1500 volts, and we see new industries adopting that as well, like the megawatt fast charging standards with the 1500 volt DC link. So typically in the past, most people, to be able to address this, have used IGBTs, 1200 or 1700 volt IGBTs in a 3-level configuration, just to be able to handle the bias. What we see is, the 3-level ANPC style of module or topology effectively halves the DC link. They still get to use IGBTs that are relatively modern. But the problem is, that 3-level adds more complexity, more devices, more points of failure. So with the wide bandgap nature of silicon carbide, we're able to create, a 2300 volt class of product to be able to directly address the 1500 volt in a 2-level configuration. And we've done that with the inexpensive, very small power module that enables, designers operating off of 1500 volts to be able to go in and within a matter of weeks, create a very simple 2-level configuration, not having to address the challenges with 3-level, being able to save on DC link capacitors. We think with silicon carbide, especially in a reasonable package, it becomes very quick to be able to install this kind of power by simplifying dramatically the system level requirements. So that's kind of the summation of the article.
Yeah, but what are the trade-offs of utilizing 2300 volt 2-level versus 1200 volt or 1700 volt 3-level topologies?
Yeah, so when it comes to 2.3 kV versus 1.2 or 1.7 kV IGBTs, the big advantage is we're able to switch significantly faster compared to the IGBT style of modules, and because of that, I would say the delta between cost has come down dramatically. And so what that's enabled our customers to do is go from like a multi-level silicon-based system, right? Give higher power and higher efficiency for lower cost by switching to silicon carbide. So just by switching the semiconductors, they're able to save, thousands of dollars in the rest of the system. So the 2-level 2.3 kV it's a little bit more expensive for semiconductor, but at the system level, it's dramatically cheaper and faster.
Yeah. Saving a lot of money, of course, is a big issue. Yes. Because cost is almost everything besides functionality, of course. But what are the advantages and the disadvantages of a modular approach if you compare it with a single stage for ESS or solar applications?
Yeah, that's actually a really common question we get because, with the approach that we've selected with the smaller 2.3 kV module, you're looking at kind of creating building blocks in the 150 to 250, 300 kilowatt range without, paralleling devices. And what that forces a system designer to do is think in a modular approach. Some people don't like the idea that they have so many components to be able to make, 1 or 2 megawatts of energy conversion. Some people like the idea of, well, it's just a 3-phase system. I just need 3 modules, 3 larger high current modules. But what you see is once you get past, a megawatt of power delivery capability, the size of the market dramatically reduces. We're talking about, fuses, contactors, relays, all the protection. Typically, higher current modules have lower switching frequency capability because of all the extra switching loss. So for a kind of a simplified system, you see that you're adding a bunch of costs because there's not a big market for the very high power protections and auxiliary components. You're looking at one singular unit that is probably going to be lifted by a crane or a forklift. And then you're looking at just kind of a standard, but overall more expensive solution. Now, if you went with a modular approach, everything is a lot more available at the 150 to 300 kilowatt range in terms of inductors, capacitors, relays, protections, etc. So you can cost optimize a modular solution. And then the really nice thing is system uptime. So if you have modular solutions and if there were something to happen to one submodule, you can still remain operational albeit at a lower power throughput, versus if you had a big single stage and something went wrong, like that's all the power, it's gone. So there is a trade-off space.
Yeah, when you talk about the power that's gone, you also probably talk about the switching losses. And if you have a look at your article, figure 5 shows the switching losses for megawatt scale power applications. Maybe you can talk a little bit about it, because it gives a comparison between two different solutions and, of course, company solutions. Yeah.
Yeah, exactly. So what we're trying to summarize is, when it comes to, if you look at the article, when it comes to being able to minimize switching losses, one of the things that we really take advantage of with the Wolfpack is the low stray inductance. So by minimizing the stray inductance, by making a physically smaller package, you're able to switch at significantly higher edge rates while still maintaining clean, nominal switching operation. So when you are able to switch very quickly, have lower switching losses because you're dealing with less of the total overall current, it makes your subsystems extremely efficient. And if you were to try to scale that to a larger module, based either on silicon carbide or silicon technology, it scales exponentially. So having a smaller kind of subsection gives you the capability of just switching at very high edge rates to save loss.
Okay, thank you.
Yep.
So, but you don't even have a chance to drink your coffee. So
It's fine. It's fine.
have it right now. I think now you earned it. What future trends do you see in this market? Do you think the next generation systems will use higher voltages?
That's a great question. I see a lot of our customers having, solutions, wanting solutions in the 1500-volt space, but they also come and say, within the next couple of years, we think the market is going to move to 2000-volt DC link. So, we definitely see the evolution of the market going up and up and up in voltage. And really it's on us as semiconductor manufacturers to enable that with the right part selection. So there's a lot of ongoing work, I would say, with the 3.3 kV voltage node to be able to support something like a 2 kV. So that's definitely at the front of our minds. And then some of the other things is being able to offer full silicon carbide multi-level solutions for 2 kV. So that's also something that our customers are looking for and asking for. So yeah, to be able to support higher voltage, we're working on, expanding the topologies as well as higher voltage devices.
Okay, thank you. So now it's time for everybody's questions. I didn't see any questions so far in our chat. Please feel free to ask the questions you would like to get answered. In the meantime, I have a, let's say more private question. You mentioned the ESS systems, the energy storage systems. How do you think will they gain importance in the future as we go on with installing more and more renewable energy solutions? Because we don't have the old situation anymore where a nuclear power plant was running 24/7 for many months continuously. And
Yeah.
we have to have some energy as well when it's nighttime and when there is no wind at all.
That's right. Yeah, we definitely see a very large explosion in demand for EA.
I don't hear anything.
Alfred, I can text him quickly and let him know that it looks like his internet jumped.
Okay, so it's on his side.
Sorry, guys. I think
Ah.
I'm back.
Yeah, very good. So then, as soon as you'll be back, I think I can ask the first question from our chat. It is, can SIC multi-level further reduce the switching losses versus SIC high voltage solutions? However, we need you, Dan, to answer the questions.
Yeah, can you hear me? I think I'm
Yep.
back. Okay, sorry. Yes, it can be, right? So anytime you are able to reduce the DC link in which you're trying to switch, so with a 3-level solution, you're able to use lower voltage devices on a 750 volt link, right? So that can reduce the switching losses even further. The challenge is, when you have a half bridge operation, right? You're always utilizing the semiconductors in a half bridge at peak 50% of the time, right? Because you can never go above that, otherwise you'd have shoot through. So it's a very healthy utilization of semiconductors, and what that means is the cost per amp is optimized. When you start going to multi-level like ANPC and you have 6 switches, you don't necessarily always get the best semiconductor utilization. So you end up having to pay more money to be able to deliver the same overall total power. You might be able to do it with higher efficiency. So there is a cost performance trade-off.
Okay. And what is your perspective on 1500 volt DC in automotive applications? So far, we only go up to 800.
Yeah, I think we see that. I would say not in consumer EV. We see it more in the heavy industry, heavy trucking. They're already at, a 1250 volt battery. So there's going to be room on top of that as well. So, when it comes to being able to do megawatt charging, you need 1500 volts. We see now kind of the evolution of the battery voltage. We see some customers even above 1000 volt, and they're using 1500 volt, 1400 volt silicon carbide devices to switch it. I don't know if it's going to happen anytime soon, for a battery voltage to be nominal 1500 volts, but it's just kind of a question of, the design of the vehicle and, what are the trade-off spaces that they have there. So unless we're starting to need more and more power, like you do in heavy vehicles, I don't really see a big push to 1500 volt DC link for batteries in EV.
Okay. And one more question came in. Can you share with us any evidence, I mean, actual products or published projects of 2000 volt DC link designs in solar applications already, please?
We don't have anything. It's something that I would say we talk with our customers about, as they want to be, ready within the next 2 calendar years, 3 calendar years, to go online and release 2 kV solar ready components. So I'm not familiar if there is already a existing design available or not.
Okie doke. So I think that's it. We are basically totally in time. Everything is perfect. Thank you very much, Dan.
Yep, thank
We
you.
really appreciate your time. And maybe if you want, you can stay in the chat. As you have seen, some of the other participants already asked some questions. Maybe you will have questions to the other people. And now I think it's time to move on. Mike Sandwyck from CISSOID wrote a story, Overcoming SIC Inverter Control Challenges and Electric Motor Drivetrains, in our April issue as well. And his colleague, Pierre Delatte, will answer all the questions regarding it. Pierre, the stage is yours.
Yes, so Mike apologized, but he's sick, so I am taking over.
Thank you for taking over.
I have prepared a short presentation, so I'm going to share my screen. Do you see my screen?
Yes.
Yes.
Okay, so we have indeed presented an article talking about overcoming SIC inverter control challenges in electric motor drive train. So I will explain what are these challenges. So let me first explain, let's say, what are the solutions we are offering. So we are a company making silicon carbide power modules, and we do especially intelligent power modules. So we are combining three-phase power module with the gate driver to make intelligent power module. We are proposing a modular solution, so we can play on the current rating of the module in the same mechanical dimensions. And so what we are offering is not just a reference design, so it's a qualified product. So the product is qualified according to the EQG 324 standard. So it's a fully proven solution that can be directly used in inverter design. And we even went a step further by adding on top of the IPM a control board. So for that, we have a partnership with a company called Silicon Mobility. And so we've built a control board around this solution. And the microprocessor we are using there, it's a mix of ARM core and some FPGA-like function, which is very useful and let's say high performance to drive a SIC inverter, because in the programmable logic of the microprocessor, you can implement the real-time control loop, and so you can let's say control the motor at high frequency, and you can implement high frequency control loop and also react very fast to fault event, which is very useful to achieve the functional safety requirement. And so this solution that we call inverter control module is certified to ISO 26262 standard by SGS TÜV. So and so we have the ASIL-C ready certification. And let's say with this hardware module, we are also offering software that is optimized for the control of electric motor. And the software is also certified for functional safety. And finally, around the inverter control module, we are proposing a complete inverter reference design. And thanks to this reference design, people can test the solution in front of an electric motor, let's say in less than a week. So we provide on-site support. We plug the characteristic of the motor into the inverter. We calibrate the inverter, and let's say in few days we are able to run the motor in different load conditions. And so what we really intend to offer is something that is between a complete inverter development, that it's taking a lot of time and a lot of investment, and a black box inverter design where people have little flexibility and little access to the inverter software. Here we are a very flexible and modular solution to support the development of SIC inverters. So what are the challenges that we help to solve with our inverter control module? But first, obviously, is hardware integration. So the integration of the power module with a gate driver. So you probably know that making a robust SIC gate driver is not an easy journey. So we are solving not only EMC issue for the gate driver design, but we have also a thermally robust solution. So with the gate driver able to operate up to 125 degrees C at board level. So it's relaxing, let's say, the thermal design in high power density design. So we have, let's say, high frequency real-time control unit. I explained the advantage of the field programmable control unit. We provide all the sensor interface for motor control applications, and also the communication and debug interface like the CAN interface, but also some high-speed transport for real-time and debug calibration. And as I explained, the hardware is qualified according to AQG 324 standard. We have also a highly configurable motor control software running advanced control algorithms based on field-oriented control with SVPWM and DPWM modulation up to 50 kilohertz, and with also a feature that is called dead time compensation, that is able to optimize the harmonic contents of the waveform. And finally, the solution is certified at, let's say, microprocessor level, software level, and module level for functional safety. And finally, we also support our customer in the electromagnetic compatibility design, providing a complete SPICE model of the inverter that is able to, let's say, looks at the trade-off to optimize EMC at inverter level. Okay, thank you for your attention.
Thank you. Now it's time for questions. Please write them into the chat. In the meantime, maybe you can give us a few more details about the dead time compensation, what this means. You said short dead time compensation. What means short, and how does that work?
Let's say the objective of this function is really to adapt in real time the dead time. So when you are switching, you need always to have a dead time between the turn off of the, for example, high side transistor and the turn on of the low side. And let's say this dead time can create some, let's say, harmonics, let's say high level harmonics. And so that's, let's say, impacting the total harmonic distortion of the output signal of the inverter. And thanks to dead time compensation, you can play on this dead time to really optimize the total harmonic distortion of the inverter, and you can, thanks to that, reduce the total harmonic distortion by a factor 2.
Okay, so let's come to the first questions. What are the challenges faced by your customers developing their silicon carbide inverter?
Okay. As I explained, one of the big challenge is the gate driver design. So with silicon carbide, you are switching faster. So that's creating common mode current, and you can disturb, let's say, the operation of the gate driver. So you have to make sure that the gate driver is robust in that environment. So that's, let's say, the effect on the gate driver of silicon carbide on the gate driver side. But also when you switch fast, you also create some challenges on the motor side, because let's say high DVDT can create overshoot on the cable between the inverter and the motors. And so with, let's say, the model we've built and the expertise we are able to advise our customers in optimizing the integration of the inverter together with their motor, while let's say avoiding the potential drawback of silicon carbide related to EMC. So that's one of the challenge we see. Then we can discuss about real-time control. So we know that thanks to the reduced switching losses, you can potentially increase the switching frequency, the PWM frequency of the inverter. But to do that, you need, let's say, a powerful control unit able to work in real time at high frequency. And this is one of the solution we provide. And let's say it's a quite transparent solution for the customer, because we not only provide the control unit, but we are also providing the software running on the control unit. And let's say this software can be easily adapted and calibrated for, let's say, each type of customers, of motors.
Yeah. So if you had to say it in one or maybe two sentences, but not 10, why are people selecting your solution?
Yeah, I think I would say the main reason, or one of the main reason, is time to market, because we are helping them to reduce the development time. So they don't need to go through the hassle of developing a complete inverter. So they can really leverage on our inverter control module and build the complete inverter around it. But still, they have the possibility to tune and adapt the solution. let's say, for example, the mechanical design around the inverter, but also they can tune the electrical characteristic of the power module, and finally, they can adapt the control software.
And how do you support your customers with inverter testing?
So we field application engineers that typically spent 1 week on site at customer to help them in the calibration and testing process of the inverter together with the motor. So we first a meeting before to go on site to make sure that we have, let's say, all the characteristic of the motors that are, let's say, fit into a lookup table. And then, so we go on site, we check all the cabling, make sure that there is no EMC issue at system level. And then we make the calibration of the inverter, of the position sensor, and we can, let's say, run the motor in different load conditions, and for example, extract efficiency map of the complete system.
And how do you support your customers in terms of the last point that you show in your presentation, electromagnetic compatibility?
Yes, so we've built a complete LT-SPICE model, not only of the ICM, but also of the complete inverter reference design. And so as it is a SPICE level modeling, it's really accurate in terms of electronic modeling of the different parasitic elements. And so it's really helping to see the trends. For example, if you increase the frequency, or let's say if you change the speed of the motor, because even if this is LT-SPICE level modeling, we've also implemented the field-oriented control regulation algorithms into LT-SPICE. And so we have really a good modeling of the complete inverter into LT-SPICE. And maybe, let's say, on top of the ICM, we are also proposing to the customer solutions for the EMI filters between the DC link capacitor and the DC connections. We have also Y capacitor into the design to manage the common mode current. So there is really a system level approach to help customers regarding EMC design.
Okay, thank you very much, Pierre. We really appreciate it. But at last, I have a short question. How exactly do you pronounce your company's name?
It's CISSOID.
CISSOID. Okay.
Yes.
Thank you very much.
You're welcome. Thank you.
Thank you. So our next presenter will be Christian Felgenmacher, who was Senior Manager Application Engineering when he wrote the story. But since last week, we know that he has been promoted to Director of Application Engineering at Rohm. Congratulations, Christian. And please go ahead telling us more about compact silicon carbide module for high power density onboard chargers.
Well, thank you very much also for the congratulations to that recent promotion. And also I'd like to share the credits for these articles, of course, with my colleague Iman Fouid, who was the main author, but unfortunately could not join today. So I have the pleasure of telling you a bit more about what we've written here and maybe why. So to summarize, maybe in one sentence, the objective of this article was to illustrate how our small transfer molded modules with the fourth generation SIC trench MOSFET inside can really help to increase power density of converters, and especially the onboard charger topic that we have highlighted in this article. We took the example of an onboard charger as an application case here because this application is particularly driven by space constraints and thus power density, and at the same time cost optimizations are extremely important. The key benefit of our module that enables an increase in power density here is that there is the fact that the module allows the user to build this very compact, and that is mainly due to two reasons. The first reason is, of course, that compared to a discrete device, the user does not have to care so much about the careful design of the cooling interface, because only one module needs to be attached to a heatsink for a particular conversion stage. For example, a 6-in-1 bridge for the input PFC stage. And then another important aspect in the thermal design, namely the electrical insulation that is already being taken care of by the ceramic insulation in the module. Another benefit, of course, is that by placing multiple chips inside a single transfer molded module, we can place them in much closer proximity as would be possible using discrete devices, for example. After all, we have to remember that discrete devices are still very common also in onboard chargers. And also, if we were to look at the module physically, if we had it in hand now, we would see that it's actually not much bigger than two large discretes. So, for example, two TO247 lead. But we can fit up to 6 logical switches in there, and that, of course, helps bring the overall size of the system down. What also helps here is not just the module form factor as such. It's also possible to switch our 4th generation SIC MOSFETs and turn them off with 0-volt external voltage applied in the off state. And that has benefits, for example, for the gate drive circuit. So you can design a unipolar power supply for each gate driver, which additionally also saves some space on the PCB. And all in all, the article, of course, does not talk just about the mechanical form factor. We also give access to some switching loss data that was already obtained from this new module type in our internal double pulse testing. And we show some simulation results based on this double pulse testing data for the application level loss expected in an 11 kilowatt onboard charger stage. And we did that for two purposes, of course. Once to illustrate the performance of the module in such a PFC stage, but also to make sure that we transfer the message that this is something that the application engineering team that we have here in Europe regularly offers also to our customers as a kind of support activity. It should be noted that, of course, the article talks about a forced cooled heatsink or forced convection cooled heatsink, which is not applicable usually to onboard chargers. But I just wanted to stress here that this really just serves as a test case for showcasing that data. And also, the article focuses a lot on the PFC stage of an onboard charger, but we also talk about the different architectural versions that onboard chargers can make use of, for example, more centralized approaches or more modular approaches. And the nice thing about the portfolio of modules that we have brought to market now is that we have not just multiple topologies, so full bridge with 4 logical switches, but also 3-phase modules. And also we offer different RDS on values and even modules in which we mix the RDS on value for the individual switch. And if you combine all of that, you end up with a portfolio that can really be a toolbox for building also the DC-DC stage, for example, if you want to realize an LLC converter, or if you want to, for example, go to a dual active bridge design also to support bidirectionality. I would say that this module portfolio really supports a wide variety of use cases. And while we did talk now only about onboard charger, and that's also the topic of the article, these modules are, of course, applicable also to much different applications from both the automotive field, but also, for example, for non-automotive applications. And basically that is in a nutshell, the summary of what we've been putting into our article. Thank you.
But can you give us some examples beyond the automotive world where these modules fit very well?
Well, I cannot go into detail, but I can talk about a few target applications, of course. So in principle, these modules can also be used, for example, to drive motors of different sizes. So for example, if we talk about fans or other industrial motor applications, we can either use these modules also there in the active front-end stage, or if the application either is tolerant to high switching speeds or has a significant benefit from the lower losses, it can also be used in small to medium-sized inverters, for example.
Okay, but recently I went to see a huge tier 1, and over there they told me, automotive tier 1, they told me that they have combined the inverter with the onboard charger in a way that they do some kind of reverse, let's say, switching. So does it mean that the onboard charger will become obsolete? If yes, what do you do in terms of being part of this business in the inverter OBC combi?
Yeah, I'm also aware of such discussions, of course, and I think the key challenge there is which parts of the combined inverter system and onboard charger system can you actually make, let's say, a dual use of. So whether that is the switching bridges or some other components, that is something which our customers probably know much better. But maybe to focus on the second part of your question. Of course, we do have a lot of other form factors and also products in our offering, and we do not only target the onboard charger. We also very actively target, for example, the main drive inverter in electric vehicles, either with bare die products through multitudes of packaging options, or also with our own larger modules. So the module we see here, that is really our offering for, I would say, the small to medium power range. We do also offer packages for much higher currents, for example, to address the main inverter. So I'm personally not too concerned about integrating these two important systems together. If it brings the electric vehicle forward on a system level, I'm sure we will still find our space inside the vehicle.
Okay, thank you. I would like to quote you and your colleague because you wrote that this 6-in-1 module with 4th generation silicon carbide MOSFETs have an efficiency of about 99% at a switching frequency of 48 kilohertz. And when you use a heatsink with forced air cooling, 99%, this is pretty good. How can we even increase this? It's close to 100. What is your perspective?
My perspective is to say, I think we also hope we made this clear, is that this is only the semiconductor efficiency. So of course there are other components in the system that have losses, right? So I'm not saying that with this module you will have 99% efficiency if you include the magnetic losses, if you have losses for your control, etc., and gate driving. So this has to be understood as just the losses occurring in the semiconductors themselves. And yes, also the switching frequency of 48 kilohertz, that can be considered maybe even not that aggressive for this application. If you go to a more aggressive cooling strategy with a liquid cooling system, you would possibly also push the switching frequency to a different area to reduce your magnetic sizes, and then more losses again would occur in the semiconductors. So this is one operating point that we have simulated here. But you're fully right, there are other components, and I think there is still room for improvement within the application. And also we have to consider that that there's also 2 stages to an onboard charger. So this is also just the input stage efficiency.
So you said there's still room for improvement of the applications, and I say there's still room for asking your questions in the chat. I don't have any questions anymore, so if anybody has questions, please ask them now. I don't see anybody typing.
Maybe I can follow up your last question also with a bit of another comment in the time that people are maybe writing questions. So I think there is even room for improvement if you just look beyond efficiency. For example, I mentioned initially that one key driver is power density, but the other one is cost. So of course, as a semiconductor manufacturer, even if we can keep the efficiency at the same level, but can do that with lower RDS on chips or chips with the same RDS on for a smaller size, I would say that our customers would even consider that still a very good proposition for improvement. So I'm not concerned of running out of things to improve.
That's very good. That's exactly the attitude an engineer has to have. I think this is what drives us. This is what brings us and our society forward. So thank you very much, Christian.
Thank you very much. Yeah.
And good luck now with a new job, with even more work and
thank you.
Even more things to explore. So thank you for joining us here in our Bodo's Power System session on silicon carbide. I would like to see many of you in the next session, which will start at 4:30, and this will be about gallium nitride. Thanks for joining, and now I will hand over to Bodo.
Looking forward to seeing you in roughly half an hour, or it's 40 minutes for the GAN session. So long you can have an easy coffee break and be back at 4:30 our time.